Hey everyone. So in this video, I'd like to talk about right triangles and the distance formula. So right triangles and circles are going to appear constantly through our study of trigonometry. And before we really get into circles, I really want to begin by talking about the distance formula. And so let's build this up. So a right triangle is any triangle that contains a 90-degree angle. And so sometimes a 90-degree angle is referred to as a right angle. And this is sort of where the right triangle gets its name from. And usually when we're looking at a right angle, we denote this with a square in that corner. Right, so here I've got two triangles that are meant to be right triangles. And so in that 90-degree angle, that right angle, I can sort of label it by drawing a square in that corner. And similarly here in this second triangle. Okay, so the side opposite the right angle in a right triangle, it's the largest side of the triangle, and usually we call it the hypotenuse. So if I go back up to these two triangles up here, the hypotenuse in this first triangle is this side here. And the hypotenuse in the second triangle is this bottom side here, the side opposite that right angle. So here's the hypotenuse. And then the other two smaller sides, they're called the legs. Right, so in our picture, these two sides are our legs. And so the most common relationship you'll probably hear when it comes to triangles, right triangles, is called the Pythagorean Theorem. So it says that the sum of the squares of the side lengths will equal the square of the hypotenuse length. Right? And so here, this idea only applies for right triangles. We'll learn about an analogous idea for non-right triangles later in the course. But let's just start with this. So this only works for right triangles. And usually, if you see a triangle labeled like, if you have a right triangle here and you label it with side lengths A, B, and C, where C is the hypotenuse and A is the side length of one leg, B is the side length of the other leg, then usually you hear the Pythagorean theorem be referred to as A squared plus B squared is equal to C squared, right? So the sum of the squares of the legs is equal to the hypotenuse squared. Okay, and so this is one of those ideas that's been proved so many different times, such a famous theorem. We're not going to get into a proof for this theorem, but I definitely encourage you to look into one if you're interested. They're all over the place online. But let's use this idea to determine the missing side length of this right triangle. So here we can recognize that this is a right triangle because we see that sort of that square in that corner. We know one of the angles is 90 degrees for this triangle. And so it's a right triangle. So let me ask you to pause the video and try and determine this missing side length yourself using the Pythagorean theorem. And when you're ready, we can go over this example together. So here, one thing I want to point out is that the hypotenuse is this side opposite the right angle, right? So here, this side length of 8, that corresponds to the length of the hypotenuse. Whereas this side length of 4, it's one of the leg lengths, and then we have a missing side length, right? So let me just label it with some symbol, some variable here. I'll just call it x. But again, that's a leg length, right? So the Pythagorean theorem says that if I square each leg length and I add them together, I'm going to get the square of my hypotenuse. Right, so this tells me that x squared plus 16 is equal to 64. Right, whatever the value of this side length is, it has to satisfy this equation. This is just a fundamental truth about right triangles, is that they satisfy the Pythagorean theorem. Okay, so here if we want to solve for this variable x, we can get that squared part alone, right? We get x squared is equal to, when we subtract 16 from both sides, we get 48 on the right. And one way we can solve this equation is sort of by taking the square root of both sides, right? If I know something squared is equal to 48, then that quantity must be plus or minus the square root of 48. Right, this idea of the square root of 48, that's the number that squares to 48. Okay, so here we can simplify this a little bit further, right? We know that the square root of a number, let's say like 48, well, we can break apart square roots across multiplication. So if we know of a perfect square that divides this number inside the square root, we can sort of use that to simplify our square root. For example, I know 48 is divisible by 16, right? So I can rewrite this as the square root of 16 times 3, and we can break apart square roots across multiplication. And so I can rewrite this as the square root of 16 times the square root of 3. And the square root of 16, well, this is something that we can compute, right? This is just 4. And so here, at the end of the day, this part comes out to be 4 square root 3. And so what we're saying is that x is equal to this missing side length. It's going to be 4 square root 3. Right? And notice that we're talking about a side length, so it doesn't quite make sense to think of this negative length. So we can just disregard that solution. It doesn't really correspond to anything meaningful in this picture. Okay, so this is the exact value of our side length here. Maybe I'll write it, I'll fill it in now. This is 4 square root 3. Okay, so the next thing I want to talk about is that one of the immediate applications of the Pythagorean theorem is computing distances. So the idea is that right triangles, they can be seen so frequently in nature and naturally, and we can sort of fit them into whatever we're looking at so frequently. And so here I want to kind of take that idea and apply it to this problem. Let's determine the distance between the 2 points -2, 1 and 1, -3. So here these are 2 points. I've put them on a coordinate plane, and I want to find that length of the shortest line segment that would connect these 2 points, right? So between these 2 points, -2, 1 and 1, 3. I want to find that distance here. If you're feeling up for it, definitely pause the video and give this problem a try, but if not, we can talk through this problem together. So the idea here is that we can kind of fit a right triangle into this picture. You might see one already, but one example I can imagine drawing here is this right triangle here. Right, so here, if we can make sense of the side lengths of this right triangle, in particular the hypotenuse, then we'll know the distance that we're looking for, right? The hypotenuse in this right triangle is the distance between these 2 points. Well, notice here that this side length, it's 3. And this side length on the left, it's 4. Right, and so we know that this is a right triangle, so the square of the side lengths of the legs, when we add them together, we're going to get the square of the hypotenuse. Right, so our distance squared well, this is going to be equal to 3 squared plus 4 squared. Right, so here our distance squared, that comes out to be well, 3 squared is 9, and 4 squared is 16, so that's 25. Right, so the square of our distance is 25, and so if we were to take the square root of both sides, plus or minus the square root of both sides to solve this equation, we get plus or minus the square root of 25 is 5. And again, we're talking about a distance here. We can sort of disregard that negative possibility. Right, so here this distance is side length, this distance is 5 units. And one thing I want you to notice is that this side length of 3 on the bottom, it can kind of be interpreted as the difference between these two x values, right? This x values on our coordinate plane tell us the position of points left and right, and really we're looking at how far left and right we have to go to get from one point to the other. Right? So the difference between 1 and -2 gives me 3, right? This 3 here is 1 minus -2. And then this 4 here, we can kind of see it as -3, or 1 minus -3, right? So 1 minus -3 gives us that value of 4, right? The difference in the y values. And so here, let's go ahead and apply this a little bit more generally. So let's find the distance between the two more general points. Let's say, I've got one point, I'm going to label it x1 and y1 because, if I have a point, I've got one x value and a y value. And then maybe a second general point, maybe I'll label it x2 and y2. Right, so in mathematics, it's so often the case that we want to compute things sort of once and for all in generality so that we can sort of plug these values into our formula and come out with our answer. Right? So here, I want to be able to find the distance between these two general points, and I'll have my distance between any two points by figuring this out. Right? And so here, if I take one point, maybe I'll just plot it right here. Let's say x1, y1 is here. And let's say x2, y2 is over here. I'm looking for this distance, right? The distance between these 2 points. I want this length here. Well, we can again apply the Pythagorean theorem. Right? We want to sort of fit a right triangle into the picture that will benefit us, that we can use. And I can imagine drawing this right triangle here, where, again, our distance between our 2 points is the hypotenuse. And so here, how do we find the side lengths of this right triangle? Well, notice that this distance, it's the difference in the y values of our 2 points, right? This is y2 minus y1. Now, why is that the case? Well, notice that y values talk about points location up and down, right? And so here y2 is this distance here, right? This is the distance for y2. And y1, well, it's this distance above the x-axis, right? This is y1. And so that distance of that triangle, that length of that vertical line segment for the side length of the triangle, well, it's the difference, y2 take away y1, right? That's this segment here. That's that length there. And then we can do the same thing for the x values, right? So here, the value x2 is this measurement here, right? From the y-axis to that x position, x2. And then x1 is this distance here. Right, so really, here this is this remaining segment that would be the same as the side length of the triangle is x2 take away x1. Right, so that's the side length of that horizontal leg. And now we know that we can apply the Pythagorean theorem to get our distance, right? So we know that the side length of the hypotenuse, which is the distance, when we square it, well, we get the sum of the squares of the leg lengths, right? So y squared one leg length, x squared, or x2 minus x1 squared, right? That's the square of one leg length. The square of the other leg length is y2 minus y1 squared. And when we add those together, we're going to get our distance squared. And usually when we want a formula, in this case we want a formula for our distance, we don't want to compute distance squared, we want just the distance. And so one thing we can do to resolve this issue is we can take the square root of both sides. Right? Distance will then equal the square root of x2 minus x1 squared plus y2 minus y1 squared. So this is the distance formula. Right, and again, you can take plus or minus the square root of both sides. That's typically what you would do to solve an equation here. But because this distance, it's not going to be negative, we can just disregard that negative solution. Okay, so let's use this formula to find the distance. Between the following 2 points, 1, 2, and 4, 5. So pause the video, go through this example yourself, and we'll go over it together when you're ready. So here, we know that the distance between these 2 points, well, it's going to equal, here maybe I'll call this point 1, and I'll call this point 2. Right, so our distance comes from the square root of, well, x2 minus x1, so here maybe I'll say this is x2, this one's x1, right, so 4 minus 1 squared plus y2 minus y1, so 5 minus 2 squared, so 5 minus 2 squared. Right, so this is the square root of, well, 4 minus 1 is 3, and then 5 minus 2, that's also 3. And so 3 squared is 9, 3 squared is 9, we're adding those and then taking the square root. So this comes out to be the square root of 18. And then we can do our same simplification, right? I know that a perfect square that divides 18 is 9, right? So I can rewrite this as the square root of 18 is equal to the square root of 9 times 2. And I could break apart square roots across multiplication, so I have the square root of 9 times the square root of 2. And so this is equal to, well, this is equal to 3 square root 2. So the distance between these 2 points is 3 times the square root of 2. One thing I want to warn you about before we close this video, before we wrap up this video, is a common error that appears when students work with square roots. So one thing I want to emphasize is that square root of x1 or x2 minus x1 squared plus y2 minus y1 squared, this is not equal to the square root of x2 minus x1 squared plus the square root of y2 minus y1 squared. Right, so what idea are we emphasizing here is that we can't break apart square roots across addition. Right, so above, we saw examples where we broke apart square roots across multiplication. We can break apart square roots across division, but we cannot break apart square roots along addition and subtraction. Right, so maybe an explicit example to showcase this using cold hard numbers is if I have, let's say, 9 plus 16, and I take the square root of that. Well, the square root of 9 plus 16, that's the same as the square root of 25, which is the square root of 25 is just 5. But what if we were to take the square root of 9 plus the square root of 16? Well, the square root of 9 is 3, the square root of 16 is 4, and so we get out 7, right? These are not the same thing. Right, so they're not the same, and this is kind of a justification for why we can't do something like this.